Well, let's look at how one of those process-based concurrent servers work. So remember, the idea here is we are going to have a server accepting connections, uh, and it might take some time to handle the connection. We don't want to make all of the other clients trying to connect wait for us. So the way we do that is, well, we still have that loop we saw before where we call accept. Then after we accept a connection, that gives us a connected file descriptor, we can handle it. But after we accept the connection and the accept system call returns, the server now forks. So it creates a child process. In the parent process, it keeps going. It calls accept again, waits for that to return, and when that happens, it calls fork again. So the loop from the parent's point of view is pretty simple. Call accept, fork, call accept, fork. We'll see there are one or two more details we have to handle. But that's the general idea. Then in those child processes, we have the connected file descriptor, that accept return. So in the child process, we can read and write from and to the client. And then when another connection comes in, while we're still handling that client in this child process, the parent process can accept, call fork again, and now we have a separate child process which does the same thing. Calls read to read something from the client, calls write to write the response back, maybe closes the connection at some point. So these two clients are interacting with the server concurrently. They're not interacting with one process concurrently. They're interacting with two separate processes, the child 1 and child 2. Actually, three. Their call to connect is handled by the parent, and then once the connection happens, everything else is handled by one of the child processes in the server. So let's take a look at the code for that. This is, again, in Lecture 17 code in echo server P. P here for process. So in main, we get our listening file descriptor in the same way. There's something here I'll talk about in a minute. Then inside our loop, we again call accept. Then rather than when we get an exception or when we get an acceptance or when we get a connection, calling some function to handle that connection, instead we fork. Now the fork system call can return either negative if there's a failure. Well, this capital F fork is a wrapper from the CSAPP library that just prints an error message and aborts if that happens. So the two other cases, the two normal cases, are in the child, fork returns 0, so everything inside the CIF is the child, and in the parent, fork returns non-zero, and we can do whatever we need to about the child process. We could call wait, for example. But here we don't want to wait. So in the parent, we call accept, we call fork. We don't do this if because that's for the child. We close the connected file descriptor. I'll talk more about that in a minute. And we repeat the loop. So we're just calling accept, fork, and also this close in a loop. In the child process, once we have this connected file descriptor and we forked, in the child process, we will close our listening file descriptor. Well, the child process isn't going to be listening. That's the parent's job. If they were to both listen, we might run into problems with not knowing which one of them is going to actually handle a particular connection. So the child process will just close that listening file descriptor altogether. It still has its connected file descriptor that it can communicate with this client that accept just gave us. So in the child, we call echo. It does all the communication it needs. Once that's finished, and if you remember from the network programming videos, this echo function just returns when it gets an end of file, meaning the client has disconnected. Well, once that happens, the server, the child process in the server, can close that connected file descriptor and then exit. This exit is important. If we didn't do that, then the child, after handling the client, would then come back here and go into the loop. And now, again, we'd have two processes running this accept loop. We only want one the original parent process. So there are a couple of things to note here. One is that we're doing a little more closing than we might expect. So why is that? Well, remember we have, after accept returns, two file descriptors. The listening file descriptor, the only thing we can do on that is to call accept some more. And the connected file descriptor, this is the one we can read and write on. When accept returns, we're still only in the parent process. We've only got one process. Then we fork. So now both processes, the parent process and the child process, have two file descriptors. One for the listening file descriptor, the listening socket, and one for the connected file descriptor, the one that the communication is going to happen on. If the child process didn't close the listening file descriptor, but also didn't call accept, which it doesn't, then this actually wouldn't be too much of a problem. When a new client connection comes in, it will be accepted by the parent because the parent's the only one calling accept. Yes, the child would have that file descriptor open until it exits, in which case, like all file descriptors, it's closed. So that might not be so terrible. But what is terrible is if the parent didn't close the connected file descriptor. The thing here is, in the child, it was not terrible if we didn't close the listening file descriptor because we're going to exit pretty soon. It might actually be a while, depending on how long echo takes to work, which depends on what the client does. But it will happen. We will eventually exit. On the other hand, in the parent, we're not planning to exit. We're planning to just repeat this loop over and over again, maybe until someone externally kills our process by sending it a signal. So if we didn't close the connected file descriptor, we'd have two problems. For one, we'd have this open file descriptor that would just be here for the remainder of the life of the parent process. Eventually, we'd run out of slots in our open file descriptor table, or we'd run into limits set by the operating system for security reasons, and we just wouldn't be able to open any more file descriptors. That would be pretty bad. We wouldn't be able to accept anything again because accept would tell us there are enough file descriptors to give you a connected file descriptor. But even worse than that, when the child process calls close, it closes its file descriptor, referring to the connected file descriptor. It exits, but this file descriptor only has the two connected file descriptors, the one in the parent, the one in the child, are pointing to the same open file on the operating system. Meaning, when we close it in the child, that doesn't actually close the connection because we're not the last person to have that file descriptor open or have that file open. Someone else does, the parent process. So when we call close, that connection wouldn't be closed. Now, the child or the client has already probably closed its end of the connection, at least for the echo server or for the echo protocol it has. But even so, this means we're keeping network connections open for potentially a really long time, as long as our server is running. Eventually, again, we're going to run into limitations set by our operating system. If we have one client trying to connect to us several times, you can imagine a web server would do that quite a bit. Every tab you have open, or for that matter, depending on the version of HTTP, every file that you access from the server, and there may be many on a single web page, will create a new connection. And, well, if that happens, we're eventually going to have all of these half-closed connections. We've closed it, but the server hasn't yet. And the operating system still keeps those around because something might happen. We might get a message back from the server saying there was a problem with closing the connection, and we'd like to be able to handle that. Okay, so we have to close the connected file descriptor in the parent. That makes sure that the client is the only one who has that file open. that socket open. So when, or not the client, the child process. So when the child process, the one talking to the client, closes it, it's done, it's finished. All right. So those were two things: handling the closing the file, the listening file descriptor in the child, closing the connected file descriptor in the parent. But there's one more thing you may have noticed that I didn't talk about yet. This call to signal. Um, well, why are we doing that? Well, there's something else. If you remember how creating a child process works, if you're working on or finished program 4, for example, you remember there's a fork in program 4 in the child process we called exec. Here we're not executing a separate program. We just are calling another function in our program, but we're exiting. But what was the other part? Yeah, in the parent, we were supposed to wait for the child to finish. If we don't, we get zombie processes. We get these processes that still take up space in the operating system's process table, still take up a maybe small but non-zero amount of memory until the parent calls wait, or until the parent dies, they're reparented to init, and init calls wait. But we're not doing that. Well, this signal handler is actually doing that for us. So remember, signal sets up a signal handler. When a particular event comes in from external to the process, usually, it will have a signal number associated with it, sig_seg_v, for example, for a segmentation fault, sig_int for control C, which you're handling in program 4, and in this case, sig_child. Which is missing the I, but that's how it's named. So sig_child, that signal is sent to a process whenever one of its child processes terminates, whether that's through a normal exit or through control C, and it turns out in a few other ways as well. Well, wait a minute. Signals, usually when they come in, if we don't do anything about them, kill the process. We don't want the parent processes to die just because their child processes die. And in fact, we know that doesn't happen. We looked at some examples and saw what went on. Well, it turns out the default handler for sig_child is to ignore it. So if we aren't doing anything specifically with sig_child, when the operating system sees, oh, a child process died, let's send a sig_child to its parent, the parent has the signal ignored, so nothing happens. It doesn't do anything. It's not. It's potentially not even interrupted. But here we are giving it a handler. We're not passing sig_ign, which means ignore. Well, that's the default anyway, or sig_dfl for the default. We're passing in a function pointer. So let's take a look at that function, sig_child handler. What's up here? Now we're passing in a function pointer, but actually from the looks of it, we're just giving the name of the function. Well, in C and C++, if you use the name of a function in an expression, it turns into a pointer to that function. So this is similar to the way the name of an array will decay to a pointer to the first element of the array. In the same way, the name of a function will decay to a pointer to the function. So this is a function with the usual signature for a signal handler. It takes an integer argument, which is the signal. We're not actually using that here, but we need to take an int for us to be able to pass that pointer to signal. We return a void. And what do? Well, when we get a signal, we call a loop with wait PID. Well, wait PID means to wait on a particular process, and we didn't even save the child process's process ID in a variable. Well, it turns out with wait PID, if you pass a negative number, it will do different things. We can look at the man page. And we see the call wait is equivalent to, oh, wait PID with -1. Well, what does -1 mean? The value of PID can be a negative number. Wait for, or, well, it can be less than -1, which it's not. So wait for any child process belonging to a particular process group. This would be used in a more advanced shell if you were handling background jobs, and being able to suspend a foreground job by pressing Control Z and so on. We're not doing that in our shell. Even in the bonus, you don't have to handle that. But -1 means wait for any of our child processes to terminate. Well, why do we call wait PID instead of wait? Well, the reason is this third argument. Wait takes just one argument, a pointer to the exit, to an integer that will get the exit status or the terminating signal of the process. Wait PID takes 3. In addition to taking the process ID, which can be -1 as we saw, it takes a set of flags ORed together with bitwise OR. Here we're passing in one flag, which is W no hang, which means don't block. If there isn't a child process running at all, if there isn't a child process that has already exited, then rather than waiting for one to do so, just return something. And if we look at the man page again, we see return immediately if no child has exited. Return value, wait PID on success returns a process ID. If W no hang was specified, one or more children specified exist, but they haven't changed state, they haven't exited yet, then return 0 on error, return -1. So if there weren't any child processes waiting to be reaped, then we would return 0. That will end the loop, and we'll just return from the signal handler. Well, why did we do a loop here? If we get a sig child every time a child process dies, it should be enough to just call wait PID once in the signal handler. Well, the problem is while we're handling one signal, another child process might die. And while we're handling a sig child, other sig childs are blocked, meaning we won't necessarily find out about those other processes. So the signal handler won't get called multiple times, but only once. So we do need to call it in a loop, just in case while we were busy handling wait PID, another child process died. Then the second call to wait PID would also return a positive number. We'd repeat the loop, and we just keep going until there are no more terminated child processes left. So wait PID is one of those system calls that you are allowed to use inside a signal handler, which is good because we are doing so here. So with that in place now, we see how we handle the missing stuff. Our loop doesn't handle the wait because we don't want the parent process to block. But when we're told that a child process is terminated, we'll wait for it. And just in case we missed one because we were waiting for that child, we were reaping it. Just in case we missed another one while we were doing that, we call it in the loop. Okay, so that is the process-based echo server. So again, a schematic diagram of what's happening. We start out with the server with the listening file descriptor. The client makes a connection request by calling connect. The server splits in half by calling fork. Each half, it has 2 file descriptors, but each half closes one of them. The parent closes the connected file descriptor. The child closes the listening file descriptor, and the parent and child, or the client and the child, are free to communicate while the parent goes back to listening for more connections to come in. So there, as I mentioned, there are a couple of issues there. We have to reap the zombie children. The parent must close its copy of connected file descriptor. But of course, those are just matters of being careful. But there are other problems as well. So there is an additional overhead from doing this, because when we create a new process, it needs, even though it has a copy of the parent's address space, and even though that's usually done copy on write, so most of it is shared until we actually do something, well, we are going to be doing some things, so we are going to be using additional memory. Um, and also, we're going to be taking up an extra slot in the process ID table. We're going to be taking time for that fork to happen, changing around the um, virtual memory tables, both when we call fork in the first place and as we do things in the parent and child, and as the operating system does context switches between the parent and the child. All of that takes time and um, CPU speed. So that's some overhead, which could be a problem. And we have two separate processes now, two copy on write shared, but really separate address spaces. They can't, the child can't just set a global variable and have the parent see that. So if we want to share data between multiple children or between the children and the parent, for example, a shared connection to a database, we're going to have to do some extra work to handle that with inter-process communication. The nice things about that are that, of course, we handle multiple connections concurrently. We don't have that problem we saw in the iterative Echo server. It's fairly clean model for sharing. Global variables aren't shared. File descriptors aren't shared because, remember, the parent closed the connected file descriptor, the child closed the listening file descriptor. The file tables are shared between different processes. So it's pretty reasonable. There's a reason processes were designed the way they are. It does make communication difficult, but it also makes things very clean in that we can't accidentally have one client interfere with another. And it's fairly simple and straightforward to execute compared to the iterative client. The only differences were we had to call fork and check its return value. We had to call a couple of extra calls to close. We had to exit in the child process, and we had to set up that signal handler to wait for child processes. All of which is going to be pretty much the same every time you do this. It's just a few lines of code, so not a big deal. So are there ways we can get around these last two problems? Well, let's see. The idea there is to have event-based servers. I'm not going to go into all of the details about that, and there isn't a code example for that in the Lecture 17 code, but you can find more information in the book, and I believe there is some example code for this on the book's website, which is linked to near the top of our Canvas page. But the idea is we have one process now, which is maintaining a set of connections, which is probably going to be an array of file descriptors. One file descriptor for each connection we've accepted. And then remember, we also have the listening file descriptors. So in a loop, this process is going to use select or epoll, so one of these functions to do input-output multiplexing, to wait for one of the file descriptors to have something happen. Either a connection attempt coming in on the listening file descriptor, or a child wrote something to it, or a client wrote something to us on a connected file descriptor. When that happens, we will from select or from epoll find out which it was, and then do the appropriate thing. If it was a listening file descriptor, then we call accept. Gives us a new connection, a new connected file descriptor. We stick that onto the array, and we keep going. If it was a connected file descriptor that had something happening, then we'll call a function or do something to handle that. So that would be a message coming in. If it's the Echo server, for example, we would reply to that message by writing out a response on the same file descriptor. So again, with select, the way that works is we have some number of active file descriptors. These are ones that haven't been closed yet. Some that are inactive. If one of these file descriptors has been closed, we don't need to wait for anything to happen there. And then some that maybe have never been used. If I've only had 7 clients try to connect so far, then connected file descriptor 7 through 9 aren't in use. The listening file descriptor is also active. When we call select, it returns some subset of those active file descriptors that have pending inputs, have something waiting to happen. So it might tell us that file descriptor 3, 7, 12, and 5 have something going on. In the server, we would handle all of those, again, in different ways depending on whether it's a listening file descriptor or a connected file descriptor. So that's kind of nice in that we only have one logical control flow. We don't have fork. We don't have code running concurrently at all, really. We're kind of hiding the concurrency in some way. You can, if you have a process like this, run a debugger on it, single step it, watch everything that's happening one step after another, because it is sequential. If we tried doing that with our process-based server, then depending on what settings we passed in the debugger, we'd either end up only watching a series of calls to accept, to fork, which always return non-zero because we're in the parent, to close, and then back to accept again. Or if we set up our debugger to follow the child process again, well, we'd be watching what happens in one child process and ignoring all of the other connections coming in or that have already come in. The other advantage is that there isn't the overhead that's inherent in creating multiple processes. So we don't have to worry about the memory taken up by those extra processes. We don't have to worry about the CPU time spent doing context switches between those two processes, changing around the virtual memory tables for the separate address spaces. And even threading, which we'll talk about in a later video, in the next video, does have some overhead of its own. So by being able to avoid that, we can actually make things go pretty quickly. Now, we are still limited to one processor, meaning in a very, very high performance situation where we're expecting enough connections to come in that that we're likely to be using up an entire processor, we might want to go with something else. But even for some high performance web servers like Nginx, Node.js, a JavaScript-based web server and framework, Tornado, something similar in Python. Nginx is a web server written in, I believe, C. All of these things use event-based servers, use the select mechanism. In something like Tornado in Python and Node.js, that's because Python and JavaScript have somewhat limited support for multiple threads. It's not that they don't support them, but there is a lot of locking that goes on that we'd be best to avoid. We'll hear more about locking when we get to the chapter on synchronization. Nginx is just designed to be really low resource, really fast, and well, if you don't have to create all of these extra processes, that's great. That said, the Apache web server, for example, which is doesn't have a reputation for being as fast as Nginx, but is still a very robust, very commonly used web server, probably more common than Nginx, does, depending on the configuration, use either process-based or, as we'll see later, thread-based concurrency. And sometimes you can use a hybrid of these. You don't necessarily need a separate process for each child. You can maybe have each process handles some subset of the children. And in that way, you get some of these benefits, but also some of the disadvantages of each side. Well, the problems with event-based server is it's a lot harder to do. With fork, you can just kind of call fork, do a little bit of closing, and then the two processes can forget about each other. In the child process, we're just doing a loop where we send something to the server, we read the response, and maybe a few other steps in between. But we don't have to worry about all of these other connections. They're not our problem. In event-based servers, we do have to worry about all of that. If we don't call select again pretty quickly, we're going to have problems we're going to have problems because some of those connections are going to start piling up, or some of those communications coming in from the client are going to start piling up. So we need to usually implement our code in such a way that we try to minimize the amount of work we do in a blocking way, in a way that waits for that work to finish. Well, reading and writing tend to be that way. We have to maybe, instead of writing a loop, write the body of that loop in a separate function and then call that function from multiple different places, but also have ways to call the same function but pass in a different client so that we can maintain all those different clients. It's hard to provide fine-grained concurrency, so we can handle one line of input from the client and maybe do whatever we need to do, or maybe one request from the client, do what we need to do. But it's pretty difficult if we need to be able to partially handle a request and then go on to the other go on to one of the other children, partially handle its request. So there's not as much latency involved. In that case, well, we might have to add some timeouts to our call to select and add some additional code to keep track of all of that. Implementing an event-based server like this, it does usually, once it gets beyond a certain level of complexity anyway, involve drawing out a state machine for what you want to happen and making sure that that state machine makes logical sense, maybe even mathematically proving it, before you go on to implement it. And it means that someone without a good feeling for the architecture of the program, maybe a new person on your team, for example, comes in, makes some tiny change inside one of these functions, and it has unexpected ramifications elsewhere. And as I mentioned, the other disadvantage is that we can't use multi-cores or multiple cores in event-based servers, at least not without doing a lot more work and really making some kind of hybrid. All right, so those are the two. Those are two of the ways, the ones that involve processes for handling concurrent network connections. So in the next video, we'll take a look at threads, thread-based servers, and what the idea is. So see you soon.